Welcome to Spring LIB.
So we're trying to find a function for the angular displacement as a function of time. We can say that we can actually, so this would be the system that we're working with. And so we can first say that the sum of the torque, the net torque, would be equal to the moment of inertia times the angular acceleration. This would be equal to minus mgl sine of theta, and this would be equal to I, the moment of inertia, times the second derivative of the angular displacement with respect to time. So that's simply just the definition of the angular acceleration. And if the angular displacement is limited to 15 degrees, so if this right here, if theta max simply equals 15 degrees, we can make the small angle approximation and say that sine of theta is approximately equal to theta. Therefore, minus mgl theta would be equal to I d, the moment of inertia times the second derivative of theta with respect to time. So we can say d, the second derivative of theta with respect to time, would be equal to negative mgl over I times theta. Let's get a new workbook here and say that the second derivative will then be equal to negative mgl over ml squared, the moment of inertia, times theta. And this is just going to equal negative g theta over L. We can notice that this is modeling simple harmonic motion where omega squared equals g over L. So given that this models simple harmonic motion, we can use equation 14.4 and say that theta equals theta max times cosine of omega t plus phi, the phase constant. And so theta will equal theta max times cosine of t times the square root of g over L plus the phase constant. And so this would be our final answer. That is the end of the solution. Thank you for watching.